Good day and welcome back for our first part of the discussion on tangent planes and linear approximations. And the general goal of this section is to first define the tangent plane, work through several examples, which we will do in this video, and then in subsequent videos we will investigate how we can use it to approximate a function value. But the nice idea is that it very much builds upon what we've done in Calculus 1 with that same exact concept of a linear approximation. So just recall from Calculus 1, a tangent line at x equals a approximates a function near x equals a. And let me see if I can represent this graphically. If we go up to the curve at x equals a, we can draw the tangent line. And what I want to observe is if I imagined zooming in on my screen as closely as I can around that point. So typically I would say imagine you're looking at it under a magnifying glass. We're zooming in. What's going to happen is that the blue curve representing our function is going to start looking more and more linear, so that in a sense the tangent line almost becomes indistinguishable from that curve. That is, the closer and closer we zoom in, the better and better the value or output of the tangent line approximates the output of the function. And let me just kind of remind you from Calculus 1 that the equation of this tangent line, if we call this point a comma b, is given by y minus b equals f prime of a x minus a. And in a moment it'll be nice to reference back to this equation. But for now, let's go ahead and move on to and introduce the concept of a tangent plane. The idea is that we're starting off with a function of two variables, f, and if we write z equals f of xy, that gives the graph of the function of two variables, or think this corresponding surface sitting in three-dimensional space. And what we would like to do is determine what is the tangent plane at this point P, x naught, y naught, z naught. And to get us to the tangent plane, I'm going to remind us of a few things we discussed in our previous section. I'm going to once again say that C1 is a curve that we get in the y equals y0 trace. And this should look similar to our previous section. If we look in that y equals y naught trace, we have a curve. We'll call this C1. And the big observation that we made about this curve is that at the point P, in that y equals y naught plane, there is a tangent line. I'm going to call it T1 for tangent line. And the slope of this tangent line is the value of the partial derivative with respect to x at that point x naught, y naught. Also recall from our previous section, we could let C2 be the x equals x naught trace. That is, we look at where does the x equals x naught plane cut through the surface. So there's some curve, let's think of it as C2, and recall that in that x equals x naught plane, at the point P, this curve C2 has a tangent. We call that T2, and the slope of the tangent is the partial with respect to y at x naught, y naught. And the observation that we can now make is T1 and T2, these lines that intersect at the point P, determine a plane. So T1 and T2 determine a plane. I will not try to draw the plane in because I think it will complicate the picture more than is necessary. But the plane that they determine is the tangent plane at P. And this is exactly what we've defined at the bottom of the page. The tangent plane, which I will oftentimes abbreviate with a capital T, capital P, to the surface S at P is the plane that contains those tangents T1 and T2. And the really nice thing is that we can write down the equation of that tangent plane. Let me note that the point P we said is x naught, y naught, z naught, with, recall, z naught is the function output associated with that input x naught, y naught. And I'm going to write down the first part of this tangent plane, and then we'll make an observation. Z minus z naught is equal to the partial with respect to x at that point x naught, y naught, times x minus x naught. And this is the portion of the plane which is going to correspond to the y equals y naught trace. That is, note, it's really the equation of the tangent line T1. So this describes T1. And if we look way above to our beginning observation, this looks very similar to that standard equation of a tangent line we encounter in Calculus 1. Y minus the y value is the slope given by the derivative, x minus the x value, which is essentially what we see. Now, in order to get the equation of the tangent plane, we must continue on and simply write the corresponding term for y. And if we would like to find the equation of a tangent line at a point, x naught, y naught, z naught, note we essentially need to determine two quantities, a partial with respect to x and a partial with respect to y. So let's go ahead and investigate a few examples. For our first example, we will find an equation of the tangent plane to the surface at this point 1, 1, 2. And to get started, I'm going to go ahead and write down a generic template for the equation of this tangent plane at the point 1, 1, 2, which corresponds to x naught, y naught, z naught in that previous definition. So we would have z minus z naught is equal to some number, which is yet to be determined, the partial with respect to x at 1, 1, times x minus x naught, plus some other number, which is yet to be determined, the partial with respect to y at that point 1, 1, multiplied by y minus y naught. So as claimed, we essentially have two values that we need to determine. Those partials evaluated at the point 1, 1. So doing some quick computations to the side, our function is given by this quantity which is equal to z, 4 minus x squared minus y squared. So the partial with respect to x, we treat the 4 and the minus y squared as a constant. Similarly, the partial with respect to y is minus 2y. Once we have these partials computed, note the partial with respect to x evaluated at 1, 1 is minus 2, and the partial with respect to y at 1, 1 is also minus 2. And substituting those values, we now have the desired equation of the tangent plane. Z minus 2 is minus 2x minus 1 minus 2y minus 1. And I would recommend leaving the equation of the tangent plane exactly in this form because I can now clearly read off the point 1, 1, 2 along with those desired values of the partials with respect to x and y. And I think this gives a good illustration or template for finding equations of tangent planes. It really is a highly computational question at this point. And we are now at a point where it's a great opportunity for you all to do a little practice. What I'm going to ask is for you to pause the video, take 3, maybe 4 minutes, and find the equation of the tangent plane to the surface at this specified point. Okay, assuming that you've paused your video and done a few computations, we have our function f sub xy, and we have our point x naught, y naught, z naught, just to make that correspondence as clear as possible. So similar to our previous example, we kind of have this template we can start with. Z minus 8 is equal to some number, which is yet to be determined, times x minus 1, plus some other number we need to determine, times y minus 4, where that first quantity would be the partial of f sub x at 1, 4, and the second number would be the partial f sub y at 1, 4. So doing a few computations to the side, f is given by y natural log x plus 2y. Its partial with respect to x, so treating the y's as constants, is simply y over x. And its partial with respect to y, now treating the ln of x as a constant, would be natural log x plus 2. So the partial with respect to x at 1, 4 is 4 over 1. And the partial with respect to y at 1, 4 is the natural log of 1 plus 2. And recall that the natural log of 1 is a common value, which is 0. Substituting in those quantities, we now have the equation of the tangent plane, and you don't need to rewrite this if you don't want to, is z minus 8 is equal to 4 times x minus 1 plus 2 times y minus 4, which completes the example and the material for this first part of the discussion. In the next video, what we'll do is dive more into the geometric visualization and think about this idea of linear approximation. So stay tuned and take care.